In this video, we're going to explore the enthalpies of formation and enthalpies of reaction. The enthalpy of formation is the heat required in order to form 1 mole of a compound from the elements in their standard state. The superscript that looks like a degree symbol here just identifies that we are at standard conditions. And the F just stands for formation. We'll have to note for all of these calculations that the enthalpy of formation of an element is 0 by definition. And so, for example, if we are looking at the formation of water from its elements, we could look up the enthalpy of formation of that. And that tells us how much energy is required in order to form water from its constituent elements. And this table provides us with some values of just various enthalpies of formation at room temperature. So what we looked at previously with the formation of water, we see that that would release 285 kilojoules per mole. Let's remember that the standard enthalpy of formation for any element in its standard state is 0. Also, we will note that the enthalpy of formation values are typically negative, which indicates that the formation of that compound from the elements is an exothermic process. Let's look at this first example here. H2 plus F2 can react to give us HF, balanced out to 2HF. Now, since this is a thermochemical equation and our values of enthalpy are given per mole of formation, we can actually look at fractional values here. So we want to change this to 1 mole of HF, meaning we are actually going to look at 1/2 H2 plus 1/2 F2 will react to give us 1 mole of HF. And that process will release 273.3 kilojoules of energy. Likewise, though, that same process for HCl only releases 92.31 kilojoules of energy. And so the formation of HF is a more exothermic process, which means that it releases more energy, and so we can say that HF is a more stable compound than HCl. Likewise, we actually see that the formation of HI is endothermic, and so it will actually require an input of energy in order to convert hydrogen and iodine over to HI, which means that really this doesn't want to occur. We have to provide energy for this to happen, which tells us that out of these 4, HI is the least stable compound. Earlier, we looked at the enthalpies of reaction by looking at thermochemical equations. It turns out that we can actually use our enthalpies of formation in order to calculate that enthalpy of a reaction. And so to do so, our enthalpy of reaction will equal the total enthalpy of our products minus the total enthalpy of formation of our reactants. And then we also have to look at our balanced chemical equation and account for the moles in that. When you're looking at this equation here, just recall that this Greek symbol here just means the sum. And so we're looking at the sum of all of our enthalpies of formation for products minus the sum of all of the enthalpies of formation of reactants. So let's take a look at an example. Here we want to calculate the enthalpy of reaction for the combustion of glucose. The first thing we see we need to do here is to balance our equation. And so we're going to need 6 O2s, 6 CO2s, and 6 H2Os in order to balance this. And so we stated previously that in order to calculate a delta H of reaction, that's going to be equal to the sum of the delta H of formation of our products minus the delta H of formation of our reactants. And so let's look first at the delta H of formation of our products. We can see that we have 6 carbon dioxide molecules, and we're given the delta H of formation of CO2 in the problem. And so we have 6 times that negative 393.5. And we also have 6 waters. And so that gives us our delta F of formation for our products. And we're going to subtract the delta enthalpy of formation of our reactants. We see that we have 1 glucose molecule, and we have 6 oxygens, but recall that the delta H of formation of any element in its natural state is 0. Then this gives us our delta H of formation of all of our reactants. And so then we just do the math of this out, and we find a value of negative 2,801 kilojoules. And so then if we wanted to, we could just add that into our thermochemical equation. Delta H equals negative 2801 kilojoules per mole of glucose. In this example, we want to calculate our standard enthalpy of formation for octane, C8H18. So we're looking at the formation of octane from its constituent elements. And we want to calculate the delta heat of formation from that. In order to find this enthalpy of formation, we're going to use information about the combustion of octane and the energy that that reaction produces. And so when octane combusts in a reaction with oxygen, remember that all combustion reactions produce carbon dioxide and water, and we're given the delta H of reaction for this of 5,440 kilojoules per mole of glucose. And so now we do need to balance our reaction. Remember that in thermochemical equations, it is okay to have fractions as your coefficients, and in this case we'll need to, since we're given information in terms of 1 mole of glucose. That means we need to keep a 1 here as our coefficient. And so with that in mind, when we balance this equation, we get 12.5 O2s, 8 carbon dioxides, and 9 waters. Now, remember that when we're looking at delta H of reaction and delta H of formation, our delta H of a reaction is going to equal the enthalpies of formation of our products minus the enthalpies of formation of our reactants. And so now let's start plugging in these numbers. We actually know the delta H of reaction in this case because we were given that information. And so negative 5,440 kilojoules is going to equal the delta HF of our products first. So 8 times our delta H of formation of carbon dioxide plus 9 times our delta H of formation of water. And so there's our delta H of formation of all of our products. Then we subtract from that the delta H of formation of our reactants. One of those is what we are actually looking for. So we will just leave that as delta H of formation of C8H18 plus 12.5 times the delta H of formation of oxygen, and any element in its natural state, is 0. And so then, if we simplify some of this math out, we get... And so now, just working the math a little bit more, we're going to add our delta H of formation of the C8H18 to both sides. And then add the 5,440 kilojoules to both sides. Brings us to here. For a final value of the standard enthalpy of formation of octane of negative 278 kilojoules per mole. In this video, we've explored the relationship between enthalpies of formation and enthalpies of reaction. Recall that enthalpies of formation involve looking at the energy involved in the formation of 1 mole of a compound from its constituent elements. In this example here, we're looking at the formation of water from hydrogen and oxygen. And remember that in thermochemical equations, it is okay to have fractional coefficients depending on what we're looking for. In this case, we're looking at the formation of 1 mole of water. The energy involved in the formation of water would be negative 285.8 kilojoules. In other words, the formation of water from its elements would release 285.8 kilojoules of energy. We also looked at how we can find the energy involved in reactions by subtracting the enthalpy of formation of our products from the enthalpies of formation of our reactants. And this would get us to delta H values that we've seen and used in thermochemical equations. If you want some more help with delta H of formation or enthalpies of reaction, please be sure to see the website or come see me. I hope this has been helpful.